All right. By now, you have learned the basics of optimization and how to build your models, whether they are linear program, LP, or mixed integer program, MIP. I think it's now time to put them all together and solve an example using publicly available real data. In this example, we are going to combine data science and optimization to solve that problem. So the use case that we are interested in is a bike share rebalancing. As many of you have known or have seen it, maybe you're a user, these rental bikes are now everywhere and everyone uses them, whether the manual ones or the electric ones. In New York City alone, which is the largest bike sharing network, there are close to 1,600 active stations and more than 25,000 active bikes. In month of July alone, more than 3 million rides have been completed in New York City, Hoboken, New Jersey, and Jersey City. So you can see that this is a very massive network. So what is the problem? The problem that we are interested in solving happens all the time. And these bike share systems, City Bike in this example, need to deal with them on a day-to-day basis. So what happens is there are some stations that receive more bikes because people drop their bikes in those stations more often than people take bikes from those stations. And there are some that exactly have the opposite problem. So you can think of if a bike station is close to, let's say, a train station, and that is central. Maybe a lot of people come out of their work, and in the last leg of their journey to home, they want to use a bike. So that station, you can assume during the rush hours, especially evening rush hours, they can have a lot of demand for bikes. And of course, in the morning, that station can have the opposite problem, right? So what happens is, with if the number of bikes coming into a station, which we can call them inflow of bikes, and the number of bikes leaving that station, outflow of the bikes, if these two numbers are very different, they can create an imbalance in the system. And if there is an imbalance, several problems can happen. Again, maybe you as a user have experienced it yourself. You want to return your bike, but you don't see any empty dock. Or you go into a station and you want to take a bike, but there is nothing available for you. So, on top of customer dissatisfaction, this can create loss of revenue because not everyone goes to a station, tries to take a bike, and then sees no bike and go to another station to take one. No, some people change their plans and maybe they become so dissatisfied that they never want to use the system again. So, as I mentioned, this is a problem that these bike sharing systems need to deal with. Yeah, and the solution for that is they transfer bikes between stations. So let's say those stations that have a lot of bikes coming in and their inflow is larger than their outflow, they have a surplus of bikes. They take bikes from those stations and deliver them to stations where they need more bikes, right? So this balancing need to happen to get to a point that you sustain a balanced bike sharing network. So as I mentioned, a balanced network, a balanced station is one where the inflow and outflow of bikes are approximately the same. And so the bikes that are transferred between the stations are, are loaded in trucks, or especially during rush hours, where when it's not very easy to, operate a truck during a heavy traffic, these bicycle trailers are used to move to move bicycles between the stations. Then there is another area that you can balance the bikes, another way to balance the bikes in the stations, and that is you have a small reserve of bikes, and you're like, okay, I know transfer of bikes may not be very easy between two stations, especially imagine if these two stations are very far from each other. But what we can do is just, inject these bikes to some of the stations, especially those with high demand. So that's another way that you can temporarily, at least, balance the station. Now that we know the setup, what we are interested in is this. We want to use the historical data, the data from July of 2022 in New York City and Jersey City. And using this data, what we are interested in is to see what is the demand for bikes per hour per station. So we want to look at the data from July and then see, is it possible for us to predict the demand for the first week of August? And now, knowing this demand, our goal is to minimize the loss of sale. Now, how do we define loss of sale? Well, loss of sale happens due to lack of bikes when customers demand them. And as mentioned earlier, we are interested in rush hour, more specifically morning rush hour. So our analysis is going to be focused on the hours of 7 a.m. to 9 a.m. The solution approach that we have is comprised of two steps. In step one, where we need to predict the demand, we are going to train an ML model where we want to predict the number of inflow of bikes to a station and outflow of bikes to a station. So we want to know how many bikes start their journey from a station and how many bikes end their journey in a station. Knowing this, then we want to use the output of this machine learning model as an input to a mathematical optimization model. In that model, we want to decide how many bikes should be added to or removed from each station during each hour so that we can minimize the loss of sale. To make life easy and for consistency and to make sure all of us are looking at the same data, and also because the main focus of this training is on the mathematical optimization, we have already trained the ML model. You can still find how it's done in the notebook, but we have already trained it. We already took the output of it, and we are going to use that output as our starting point for the mathematical optimization model. So let's take a very quick look at how the output of ML, which is the input of MO, looks like. So we have two CSV files. One of them is the stations flow, where you have the 4 columns, and you have the information for each station, all the dates and hours during the 24 hours of the day for the 5 day of the week in the first week of August. And then you have 2 columns that one of them is called start forecast and one of them is called end forecast. Start forecast is showing you the number of bikes or the number of bikes that start their trip from that station. And end forecast shows you the number of bikes that end their trip in that station. In the top stations, we have, again, the station name and the most important other column that we are interested here is the capacity. So it just shows you the capacity of a station in terms of the number of bikes. So how many bikes actually that the station can hold. There is no reason for now to care about or be concerned about the other columns. So in the top stations, the only columns we're interested in are just the station name and the capacity of each station. Our mathematical optimization model is going to have some assumptions. The first one is we are going to only look at the top 50 stations, even though there are, as mentioned earlier, there are more than 1,500 stations. The reason we are only focusing on the first 50, the top 50, is we want to ensure the number of variables and constraints that we are creating in our mathematical optimization model are small enough so that everyone, especially those who are using the Gurobi restricted license, can still be able to run the model and follow along. As mentioned before, we know it's not very easy to move transferred bikes between stations during the rush hour. So we are going to assume there are a certain number of bikes available as a reserve for us at the beginning of each hour, and then we can allocate these bikes to different stations. And the one other thing is we are going to assume that the number of bikes available in the stations, so these are, let's call them the inventory of the stations, at the beginning of the first hour, at the beginning of the analysis, which for us, it's 7 a.m., it is going to be 0. I know it doesn't make any sense because one can say, well, all the bikes that arrive at the station at 6:59, they are still there. I know, but don't worry about it. This is not going to change anything. This is just to simplify and also throw a little bit of a curveball your way to see how we can handle situations like this, which can actually happen quite often, if not in this case, in a lot of similar cases. Right. So I want to give you some final hints about the mathematical optimization model and how you can write it. We already know what is the objective. We want to minimize loss. And we mentioned that we are going to do this by deciding how many bikes should be added to or removed from each station per hour. And I think it's fair to say that should become a decision variable. But what else? To understand what other decision variables or constraints that you should have, think about these questions that you are seeing on the slide. How do you define loss? Is there a relation between loss and the number of bikes that start their journey or end their journey at a location? Is there a relation between loss and the number of bikes that we add or remove from a station? What else? Is there a limit, whether on the higher end, which means the maximum, or on the lower end, minimum, for the number of bikes that we can add or remove from a station? We already said that let's assume the number of bikes in the station, in the stations, all the stations, at the beginning of hour 7, which is the beginning of the analysis, is 0. But how about at the beginning of hour 8? How about hour 9? Because those are part of the analysis. And you already add or remove some bikes from the system. There are some bikes that, again, come there, end their journey in a location, or start their journey from the location. Does it matter how these relate to each other? So think about these questions, and hopefully they give you some clue and what other decision variables or constraints you need for your mathematical optimization model. Good luck.